going to talk to you about Chrome internals. So I'm Darin Fisher. I'm a member of the Chrome team. I've actually been with the project since inception back in 2006. And today is just an opportunity to go through all of the stuff that's underneath the hood. And so there'll be things that you may have heard about before if you've read the comic. But I just wanted to cover as much ground as I could and discuss all the different things that go into Chrome's architecture. So this was our guiding principle from day one. We really wanted to make sure that we were stressing a very simple interface to Chrome, and that would allow people to very easily and naturally get to a very fast browser, very powerful browser, leveraging this powerful architecture, but they don't see or be burdened by the architecture. This sort of reminded us of the way Google.com search experience was, and so here's just a little image of Chrome, very simple Chrome that you've all seen. There's a little photo of taken off of one of the design docs for Chrome's architecture. Just a little aside, this is actually rendered using HTML. Actually thought I would just quickly show this because it's interesting. It's using a WebKit gradient effect on a straight-up image. So it's kind of neat that you can do all this kinds of stuff in WebKit, which Chrome is based on. Okay, so here's a little quote that I'm not really sure who to attribute it to, but back in 2006, it was something that we were all thinking about. It's at the time, modern browsers really resembled cooperatively multitasked operating systems of the past. So what do I mean? You can think back to older versions of Windows, older versions of Mac OS, where if any process, any application on your system decided to go into an infinite loop or crashed, it could bring down your whole entire operating system and you lose all your applications. And this was what the state of browsers were back then. And it seemed very unfortunate, especially as web applications were getting larger and more complicated. I mean, oftentimes you'd have the experience of composing an email and suddenly deciding, I want to go do a search, or I want to go do something else, and branching off to go get some information and venturing to a website that maybe somehow, unfortunately, triggers a browser bug, and then you completely lose what you were working on in that other tab. This just seemed like a very unfortunate situation to us, and we were just thinking, modern operating systems solve this by separation of applications into different processes, so couldn't we exploit that? And the goals of, speaking more about goals for Chrome back in the day, beyond just a simple interface, we really wanted to see what we could do to really move the bar in terms of speed, stability, and security. We felt like as applications were getting more complicated, speed was very important. As applications getting more complicated, it's more likely that you could have instability issues causing problems. And so how could we solve all these problems? Again, multi-process architecture. If we could divide the application up into multiple processes, it'd be great if you could have web apps each having their own thread. And you get this if each web app has its own process. Separate address spaces. If each web application has its own address space, its own process, then there's some insulation in case one of the applications happens to trigger a bug and cause a crash. Similarly, if your applications are consuming a lot of memory and they're all sharing one giant heap together, you can have performance problems. But with separate app processes and separate address spaces, each one having its own memory pools, you have a lot of smaller memory pools and better performance ensues. Security. So given that we're actually leveraging operating system processes, and operating systems already have the idea that a process might have certain capabilities based on the user associated with that process, seems like we could leverage the operating system's support for taking away privileges from a process or limiting the privileges of a process, and thereby achieve a sandbox to run web applications in. And this would be great because, we know that the software is just enormously complicated. And if there's any kind of bug, and that bug allows an attacker to get code running with the privileges of the user, then they can do things that would potentially harm the user because they have the power of the user. And so we really like the idea of there being this belt and suspenders, this secondary level of protection, the sandbox. And we get all this. It's all possible because we can divide the application, the browser, into multiple processes. Okay, but I mentioned before speed. Speed is very important. And so in the early days, we were thinking, it's one thing to divide the browser into multiple processes, and that allows the applications to not stomp on one another and achieve good performance there, good scaling across multiple cores. But we just want the rendering engine to be very fast as well. So that informed our choice of rendering engine, and we went with WebKit because it was, well, we knew that Chrome was going to be open source, and we took a look at all the open source options, and WebKit was just really fast, and it has a very small footprint. Back in 2006, you could see that WebKit was starting to become the popular choice amongst mobile browsers, and this all had to do with, just how good WebKit is. But there was one thing that we saw as a big opportunity, and that was JavaScript performance. Back in 2006, the JavaScript engine in WebKit was a very straightforward, simple, interpreted JavaScript engine. And we had a team at Google who recognized that there was this great opportunity to apply some of the more modern approaches to VMs to build a JavaScript engine that was JIT-based and leveraged a lot of other techniques to make dynamic programs, like dynamic programming languages like JavaScript, run so much faster. And the V8 team was very successful, in my opinion. I mean, compared to where we were in 2006, they've come order of magnitude or one or two orders of magnitude, depending on what kinds of tests you're talking about. And that's just outstanding. Don't you just love silent auto update? I do. Okay, so under the hood. The major components of Chrome. So this is sort of gives you a big picture of some of the major modules, and Chromium is the source base from which Chrome is derived, Chrome being the application. And Chromium depends on WebKit. I've mentioned WebKit already, and V8. And Skia is our graphics engine. It actually comes from the Android project. It's a 2D graphics engine that's highly optimized for mobile environments, and so it really runs well on a desktop system. And so in the Chromium world, how these are all glued together, Chromium embeds WebKit. WebKit renders to Skia. Chromium also renders its own UI to Skia. And WebKit talks to V8 to run JavaScript, but Chromium also talks directly to V8 for things like proxy autoconfig and other usages of JavaScript in a browser, besides just that related to web content. So Chromium itself, the code base, includes all the other stuff that's not WebKit, that's not V8, not Skia, and other libraries that we incorporate, but it includes things like the UI, the tab strip, and the Omnibox. These are all native UI elements. We chose to go with a native UI for Chrome because we really want to make sure that we could get all of the look and feel just right. We wanted to have a very lightweight, fast browser. We wanted to have a browser that was highly tuned for Windows, and then again for Mac, and then again for Linux. And so for Windows, we went about building this native tab strip, this native Omnibox. And however, not all of our UI is native. The new tab page, the downloads page, the history panel, these appear in the tab contents area. And so they are naturally HTML-based, so that you get the same look and feel that you would for a web app. And this turned out to work very well for us. So basically, the amount of native code is minimized to just that of the frame or the window manager. So that's pretty much all I'm going to talk about as far as UI is concerned. The other main components in Chromium, though, are multi-process architecture. That's sort of the thing that the goop that binds this whole collection of processes together. And the history system is fairly complicated, based around SQLite, and there's a full text index there. The network stack runs in the main process. I'll actually talk more about processes in detail later. And then there's a sandbox piece of module within the Chromium source base. So moving on. Multi-process architecture, just getting into this a little bit more. So I've been talking about processes. So this is what I mean. This picture here shows that there's this main coordinating browser process that all of the child processes talk to. And we have a sequence, a set of different renderers. Each of the rendering processes are the processes that embed WebKit to render web pages. And they talk back to the browser for things like I/O. So because of the sandbox, the renderers actually don't have access to direct access to the system, and they must proxy through the browser for everything. So this is sort of a hub-and-spoke design. I've shown some other processes here, worker processes, plugin processes. So worker processes are the new web workers coming that you start to see various browsers implementing. These allow for a web page to have a background thread or a background set of threads that do work. And there's a very asynchronous way of communicating to those background threads, which lends itself very naturally to having those workers be out of process. And there can be many of them. plugins. Plugins actually run outside the sandbox in their own process. So when I say plugins here, I don't mean like Firefox extensions or things like that. I mean the traditional browser plugins like Flash, Java, Silverlight, and so on that use things like NPAPI or ActiveX. And so for each of these plugins, we load them in their own process. So there's a Flash process and a Java process and so on. Now, I've made some mention here of trust, untrusted, and so on. So it's important to note that we really would like to have sandboxed plugins. We would like to have included them in the sandbox. But because they are basically already software that's on the system, they have dependencies on being able to actually access the system directly, they just can't be included in the sandbox. A good example is Flash. It actually needs to be able to auto-update itself. Well, if we denied its ability to access your system, it wouldn't be able to update itself. So it has to run outside of the sandbox. But it still runs in its own process so that we get some insulation from page faults and so on. So inter-process communication, just a few words about that. We decided early on that we really, there were many applications that you could point to that were multi-process already on your Windows desktop or wherever. And a lot of times, it's very easy to build a multi-process application that doesn't perform well. And one of the key things we really went for was this so-called apartment model, where we want to make sure that individual processes, or really individual threads, really can run as independently as possible and rely on more of an asynchronous communication. Locking between the processes, locking between the threads as minimally as possible. So we went for an asynchronous communication system. Early on, we tried using existing systems on Windows, like Windows messages, that you can do asynchronous Windows messages. We looked at using COM. All of these systems were fairly complicated, and in order to get the kind of control we wanted over the IPC, we went with name pipes. Plus, name pipes are much more portable, and we knew we would eventually be bringing this to Mac and Linux, and so it made sense to go with name pipes. We do have some support for limited blocking calls because that's required for some of the to support some of the web interfaces that we need to support. I can talk about that more later. There's some use of shared memory, but we basically don't use shared memory unless it really gives a big benefit because it just adds complexity to the system. So basically, you can imagine, if you will, these different processes that are basically having a stream of events asynchronously flowing to one process or the other, and it's sort of like a big interconnected network of data being passed around. And we're trying to keep this thing running as smoothly as possible and avoiding hiccups. That's basically the goal of the inter-process communication. This diagram here just shows that in order to keep things running smoothly, we dedicate a thread in each process to run and service the IPC. That way, if the UI thread, TUI in the browser, were to go off and produce a whole bunch of IPCs that he wants to send to the renderer, but then not yield control to the system that actually sends the IPCs, that could be bad. So instead, there's a background thread who picks up that queue of outbound requests and sends them along. Meanwhile, the browser's doing other things, possibly expensive things, but the IPC is flowing. And in the renderer, the same deal. JavaScript application could be consuming WebKit, but we still have an I/O thread that's pumping events and doing things and keeping things running smoothly. That's just sort of a bird's eye view of what the inter-process communication looks like. Process assignments. What do I mean by this? Given that Chrome has many rendering processes, and we really would love, ideally, to be able to assign a single web application to a single process, thereby giving the best separation between web applications. There's some realities to the web that force us to group some applications or some, what do I mean by applications? Web pages. Some web pages have to be grouped together in processes. And then there's opportunities to decide when we should actually create a new process. And coming up with a good formula here is a little tricky because there's some realistic limitations, like we don't want to have too many processes. At some point, you start to pay a cost by having many processes. So we have a process limit. If that limit's reached, we will start reusing processes. If there's a potential script connection between two web pages, well, they need to be in the same process. We could have built the system so that there was a complex way of a bridge or so between the script running in one page and the script in another page. But that seemed like it would be overly complicated and potentially lead to a lot of performance problems. So instead, we thought, well, a web application, well, if we think of a web application that might have many pages as probably sharing script connections, then it kind of makes sense for those many pages to all be grouped in the same process. And so this idea of just looking at any page that's open from WebKit as potentially being a page that should be in the same process, that seemed to make sense, and it works out pretty well for a lot of applications. You'd think, interestingly enough, target blank, I put this up here because you'd think that when a user clicks on target blank, and that means open a new window, that there should be no script connection between that and the page that you opened, that the link was clicked on. Well, it turns out that there is a very real script connection. When that new page is opened, it's actually got a .opener property, and the .opener property allows it to see the page from which he was opened. Now, that's okay. So, well, then in that case, if it's the same origin, because JavaScript allows scripting, provided the origin A and origin B are the same, then we would only group them in the same process if the new page is of the same origin. And that's actually not good enough, because it might be that you are clicking a link from opening a new window from origin A to origin B, but origin B might have a subframe that's also on origin A. And the page over here can actually find that frame by name. And so sort of after the fact, after a window is created, there might be a script connection that becomes established. So we need to keep those in the same process. Okay. But then there are some heuristics to try to get out of these sort of situations. Turns out that a lot of web applications use window.open to navigate from the application to a new page. For example, Gmail, when you click a link, it wants to take you to a new page for that link. And the thing, though, is that Gmail really has no interest in there being a script connection between Gmail and that new page. He even goes so far to set the opener property of that new page to null before navigating that new page to the URL that you clicked on. Those kinds of tricks are done to sort of sever the script connection, at least as far as that rendering process would be concerned. Well, we sort of use that as a clue, as a heuristic to determine that, oh, I see, there's no script connection because it's been removed. We can just fork that off into another process. And so that's the kind of heuristic that we've applied to get sort of a good distribution of processes when, say, Gmail is the source of all your new tabs because you're clicking links there, or other applications like Gmail. All right. Another topic about process assignments. When you are just typing a URL in the location bar, you're saying, replace the current tab with new contents from this new location. And we recognize that if what you're typing is a URL with a new domain, effectively, it's an opportunity for us to say, it's like closing the tab and opening a new tab. And so what you achieve there is an opportunity to switch processes out from under the system without the user really being aware that there was a process switch. And this becomes a really natural and nice point for garbage collection. So frequently in Chrome, you're just typing in the location bar, you go to enter a new URL up there, and unbeknownst to you, we're actually swapping processes underneath. Oh yes, process per domain. So some people might have heard about the research project, the Giselle browser, which basically implemented this idea of actually having a separate rendering process per domain rather than a separate rendering process per tab. This was something that we looked at very hard as well because it seems very attractive, and our conclusions were very similar to theirs. That you suffer it turns out you suffer some web compatibility hit for trying to make this kind of change, but it still seems so attractive. Wouldn't it be nice if you could have one rendering engine dedicated for one domain? Then you could start to apply some of these multi-process benefits to actual domains. You could say all the data associated to foo.com would only be available to that rendering process, and he wouldn't be able to ever see data for bar.com. So that's sort of the holy grail of multi-process architecture, but there's some real web compat challenges that we face with that. For example, third-party cookies are a big problem. It turns out the web page actually can dabble with cookies that are not its own. Okay, it's the sandbox. So I've been talking about the sandbox, but here's a little more detail about it. Primary goal of the sandbox was really all about protecting the user against malware. There's so many things that you might wish to sandbox. Like you might wish to, as I was just saying, you might wish to protect one origin from another origin, foo.com from bar.com. But that wasn't something we strove to achieve initially. The first goal of the sandbox was really just as a catch-all to protect the user against malware. If somehow there was a bug exploited in the rendering engine, it should not turn itself into a vehicle to allow people to distribute malware. So Chrome has several features, several anti-malware features. It has the sandbox, of course, but it also has the safe browsing feature, much like what you find in other browsers, where once you venture onto a URL or a page that contains content known to be bad, we'll show an interstitial, an error, allowing the user to go through or not. That's sort of a first cut, and obviously, if we don't know, if the service that you're using to supply that data doesn't know about the bad URL, it's not going to work. So you need some kind of extra protection. It was a very interesting story. One of our engineers was tracking down a crash that he saw in Chrome in the renderer, and he's like, it's hard to reproduce, hard to debug when he has the sandbox engaged. So he thought, I'll just take off the sandbox and then now load this page up in my debugger and go to town trying to figure it out. Well, it turns out that was actually a site serving malware that exploited his system and corrupted his XP. And he was like, oh, crap, now I have to reimage, just because he was trying to debug this problem. So the sandbox was really a really nice tool. What are we trying to restrict? Well, trying to restrict the processes' access to the file system and network and other kinds of devices on the system. We're also trying to restrict his access to the windowing system. So you shouldn't be able to mess around with your desktop, shouldn't be able to mess around with any of the hardware, your keyboard or your mouse, and so on. The mechanisms to achieve this, well, we can, as I said, every process has some associated user, and the user has a certain set of capabilities. Under Windows, this is represented by a user token, and we can strip all the rights off of that user token, thereby denying things like system access and file system access. And there's other techniques in Windows, including job objects, that can be used to further restrict the capabilities of a process. And even just running it on a separate virtual desktop. This is a great way to sort of limit the process's ability to get access to some of the input devices. Okay, but Sandbox actually doesn't need, browser actually needs to be able to load file URLs. So how do we achieve that, given the Sandbox doesn't allow you to access file URLs? Well, two big examples of this are A, loading file URLs, and the other one is being able to actually upload a file that is specified in a web form. So to deal with file uploads, what we do is when the WebKit wants to show a file picker, it actually just asks the browser, please show a file picker. Or our rendering process asks the browser, please show a file picker. The browser shows a file picker, the user makes their selection, and then what we do before we return that result to the rendering engine is we put it on a whitelist associated with that rendering engine. And now that rendering engine is allowed to say that he wants to upload that file. See, it's pretty simple. File URLs, well, what is this? This is, the rendering engine being able to load any file URL, because if you go to some foo.html on your hard drive, it can load images from anywhere else on the hard drive. To make that work, what we do is we actually just dedicate a separate process for file URLs. So we're never mixing web content and file URLs in the same process. And for example, if you go into the location bar and you type file : and you're sitting on a web page somewhere, what we actually do is leverage that technique I mentioned before of swapping the rendering engine out underneath the hood, so that really what we're doing is loading it in a fresh rendering engine that is now just dedicated to local files. Okay, so what isn't protected? I talked a little bit before about we're not separating origins. So what that means is that cookies, a rendering engine can read all of your cookies from anywhere. So if somehow there was a bug in the rendering engine, that guy could then go and ask for cookies from any domain. And this is just this is something we have to support because of document.cookie. There's a JavaScript API to allow the web page to read your cookies. The one exception here is the HTTP-only cookies. We actually don't have to allow the renderer to see those. He can make HTTP requests, and then the network stack running in the browser will add those HTTP-only cookies. Passwords. Passwords, much like cookies, it turns out that the web page can read the passwords. So if you have an input type equals password and the user enters a value there, it's actually supported by the web that the web page should be able to actually read that value out and do something with it. It's just a way, the input type equals password is just a mechanism for having some sort of secret that's entered into the web page. And so this generic mechanism allows web pages to do things like do client-side authentication. So it's not necessarily the case that this password field corresponds to data that will be in a forum post. The reason why that's interesting is because you might imagine a system where the browser returns a dummy password to the web page. And then when the dummy password appears in the forum post, the browser transparently replaces it with the real password. That's a very clever way to avoid exposing the real password to the web page. But again, because the web page has the power to read that value and do some computation on it, there's a huge web compatibility problem here. So we end up exposing the passwords to the rendering engine. Other things like HTML5 database, local store, session store, they're much like cookies, same kind of deal. They're origin-based, and the renderer gets access to them. Cross-site attacks, user data in the cloud, that kind of stuff is not what the sandbox is trying to protect against. You could imagine a better sandbox that did do that kind of stuff. Okay, so moving on to rendering in a sandbox. So given that we have almost no access to the system, how do we render? Normally, a web rendering engine is designed to render to a native widget, like an hwind or a NSView or a xwindow. And that kind of thing doesn't work in a sandbox renderer because we literally are trying to deny access to hwinds. Hwinds are in the Windows desktop. We're trying to deny that. So instead, very simply, render to a bitmap, send the bitmap to the browser process. Browser puts that bitmap on the screen. So it's like a glorified image viewer. Complexities. Well, the rendering engine can't get away with not using some system calls. For example, we need a way to render fonts. And on Windows, to get the best sort of fidelity and the best sort of native look and feel, you really need to use the Windows GDI APIs to render fonts. Well, an interesting story here, this turned out to be really challenging because once you take away the rendering engine's ability to access the file system, well, what this actually means is that you can't load fonts. And all the font APIs transparently under the hood will load fonts. Interestingly enough, they don't do it in user land. They do it in kernel mode. But they use the token of the process that was calling them to actually decide whether or not the kernel should load that font. Well, our token doesn't have those privileges. So it turns out that Chrome implements a glorious hack of when we encounter a font API call that fails, we pause and let the browser repeat the API and load the font, thereby populating the kernel's cache of all fonts. And then we repeat the exercise of calling that API in the renderer, and this time hope it succeeds because it hits some cache that the kernel maintains. So fascinating complexities just trying to deal with some OS APIs. Other things that we really wanted to try to achieve with this, we really want to make sure that there's no way that a hung renderer can screw up the browser. This really impacts the rendering model, which I'll talk about a little more in detail later. But fundamentally, you don't want to be in a situation where the renderer is acquiring a lock that the browser then has to also acquire because the renderer might never release it. And then as an end result, a bad renderer might bring down the whole browser, and we just really don't want to be in that situation. And of course, it needs to be really fast. So speed is very important, and somehow there should not be any situations where the renderer can lock up the browser. So painting and scrolling, lock-free painting and scrolling. This is a system that we implement of maintaining a backing store in the browser, a recent pixmap of what the tab looks like. Very simple idea. And then the renderer, whenever he needs to update a region, he sends a bitmap over shared memory to the browser, and he blitz that into his backing store, and then blitz that result onto the screen. Very straightforward. And then when the browser is finished putting pixels on the screen, he acknowledges to the renderer, hey, look, and now it's a good time to produce another bitmap. So this turns out to work fairly well, except that we recognize that you end up in this sort of staggering kind of situation where the renderer paints, then the browser paints, then the renderer paints, browser paints. And in order to get better performance, we allow the renderer to sort of prefetch or do one additional render ahead of the next, in parallel to the browser painting. So if you're on a multi-core system, you'll be able to light up both CPUs One of them is the renderer producing the next rendered output, and the other one is the browser putting the pixels from the previous rendering on the screen. Scrolling works very similarly. In order to achieve very good scrolling performance, you don't want to just repaint the whole thing. You want to tell the windowing system, hey, look, move your pixels down and backfill this exposed region. So we send commands from the renderer to scroll the backing store and fill the exposed region, and then the browser repeats the exercise of commanding the windowing system to scroll the pixels and then backfill the exposed region. And again, it acknowledges once that's been done. Actually, one more comment about painting. So whenever you need to resize the browser window, because we have a backing store of the old rendering, we don't necessarily have that backing store is not the right size when you resize. And so it turns out to be necessary to play some games to try to get good performance there, because we're in a situation where a resize happened and we want to update the backing store, and we obviously don't have it yet, but we have asked the renderer to produce the data, and we're just waiting for the renderer to produce the data. But Windows has asked us to paint right now because it just resized. So we do implement a little bit of a pause to allow the renderer to produce pixels. If it can produce them fast enough, then on resize, we will paint the correct pixels and not the old pixels. But it's fairly common in Chrome when you use it. If you drag resize very quickly, you will see a little gutter, and that's what's going on there. Resource loading. So as I mentioned before, the browser is this proxy for all the I/O. He takes great care to restrict the types of URLs that can be loaded based on protocols. So if a rendering process was not asked by the browser to load a file URL, then the rendering process shall not request file URLs. And if he does, they're denied. Chrome colon URLs are like file colon URLs in that they're trusted. Chrome colon URLs are used to load things like the new tab page, the downloads panel, and other web content that's part of Chrome's UI. This browser network code will actually perform all the safe browsing checks I talked about. He'll do all kinds of things like vending the cookies to the renderers and managing all the data associated with resource loading. Finally, before WebKit sees any data, the browser has actually performed a lot of different things. He's handled HTTP authentication if prompting was necessary. He's done all the SSL verification and potentially put up UI to ask users if they're, put up a warning dialogues like this, the certificate is not necessarily valid. He's done all these things by the time WebKit sees any data. He's also potentially handled downloads, so content sniffing happens in the browser, MIME detection happens there if necessary, and so on. Some of the things that's interesting about downloads is that if you imagine a scenario where you were returning data to WebKit or to the rendering process, and that process was to determine whether or not the data should be treated as a download, well, you would have been in an unfortunate situation of having to echo that data back to the browser so that he could save it to disk. And so moving the detection into the browser allows for better performance. All the decisions happen there, and it can either decide at that time to tee it to disk instead of to the renderer. The history system. So much like painting, it was important to us that we could achieve a good way to manage visited links without locking. We want to make sure that the renderer could very quickly check whether or not a link was visited, so it could color it as visited or not, and do so in a way that didn't require acquiring any kind of lock. So there's this simple idea of shared memory containing a bitmap that's treated like a hash table. We apply a crypto hash to the URL, take 64 bits of that, index this bitmap, and then see if the link's visited or not. Fine. And then the browser, whenever he needs to update this thing, he's either setting the bits, or if he finds that he needs to grow the table, he creates a whole new table, sends the new table down to the renderer. The renderers drop the old table and then pick up the new one. Works great, with the minor exception that it causes us to fail one of the ACID3 tests. So this is why Chrome gets that link test error in ACID3, because it turns out that this is a very asynchronous model of the browser is the only one who writes to the visited link table. The renderer is the one who reads, but this ACID3 test actually requires the renderer to have visited and be able to check right away that this link is actually visited. And we're working on a fix. So after page loads, data is actually extracted from the page so that it can be sent into the full text index, and that's what drives things like the omnibox and the whole history search mechanism in Chrome. And the new tab page is populated with thumbnails. Those thumbnails are captured at this time, and so on. And this data is collected, sent up to the browser. All this history management happens up there. Plugins. This is probably plugins supporting Netscape-style plugins and even ActiveX controls through a shim. Talk a little bit more about that. Supporting plugins turned out to be probably one of the hardest things about doing Chrome, because we knew they could not run in the sandbox renderer because they required a lot of privileges, and we knew that we wanted to have a sandbox that was very aggressive, and so that meant pushing the plugin outside of the rendering engine, which meant taking an API that was synchronous and designed to run inside of a rendering engine and forcing it out of process. So this turned out to be very complicated. But what we tried to do here by allocating a single plugin process per plugin was to give plugins sort of this environment to run in that looked to them much like an ordinary browser environment. So unbeknownst to them, hopefully, they don't realize that they're actually in a separate process. And this works. This through a lot of sweat, tears, and toil. We've gotten this to work. So there's two types of plugins, two modes of rendering for plugins. One is called windowless, and one is windowed. Windowed means that you actually get the plugin actually has its own native widget, like its own hwind, and then once it has its own hwind, it has its own render loop basically, and it has a lot of control and access to the system. But we're running that hwind out of process, and so we are managing a windowing hierarchy that spans processes, and windows outside of our control will be doing IPCs between those windows, and that leads to a lot of complexity. So we do some interesting tricks to try to minimize the synchronous communication that Windows does underneath the hood, so that scrolling a page with plugins will actually perform okay. I think we still have room to improve here, but it's gotten a lot better since the Chrome 1 days. Or I should say since our initial launch. Caching the rendering of windowless plugins. What we do when there's a windowless plugin, this is a plugin type that has no hwind associated with it, no window. Instead, the rendering engine just asks it, please paint into this buffer. And it turns out that windowless plugins do something interesting. They actually do the compositing inside the plugin. What this means is, and they can be in the Z order of CSS, and so this means is that as WebKit is painting and it encounters a plugin, it sort of stops, asks the plugin, now please draw your pixels, and then WebKit continues painting on top to get this interesting stack. And so if we're trying to achieve, as I mentioned earlier on, good asynchronous communication between our processes and asynchronous separation, here rendering windowless plugins is a case where we don't have that. So our solution was to keep a cache of what the windowless plugin rendered last time in the rendering process, so that when we're painting in WebKit, he can quickly just paint from that cached representation of the plugin. And once we implemented this, we get a much better performance for windowless plugins. Of course, you suffer a frame rate hit for windowless animations, but overall, the results are much better. The other big challenge with all of this is porting, because NPAPI is not a platform-independent API. It's really just glue, bridging glue to bind the browser to other native APIs for rendering. And so the work required to support Mac and Linux is similar in magnitude to the work that was required to support Windows, and it's very challenging. But it's coming along. The current Chromium Mac and Linux builds do not yet have plugins enabled for this reason, but they're in development and can be enabled through a switch, I believe. So I want to talk a little bit about WebKit. Just briefly about WebKit. So WebKit, for those who don't know, is comprised of, what I'd say is about three major modules. There's JavaScript core, the WebKit's JavaScript engine. This is obviously what Chrome doesn't use. We use V8 instead. Web core represents all of the code to do the HTML, CSS, and DOM rendering. SVG is at this layer, and other features. A lot of the new APIs, database, and so on are at this layer. And then there's the WebKit layer to WebKit, which is the API layer. And we don't use this because the layers that exist here in the WebKit repository are things like a COM API to WebKit, an Objective-C API to WebKit, a GTK API to WebKit, a Qt API to WebKit, WX Widgets API to WebKit, none of those were really appropriate for our use case where we needed to run the renderer in this insulated world in the sandbox where it really doesn't have access to the system. And so there's any native toolkit you can imagine, or any even cross-platform toolkit that under the hood really deals in native widgets, just wouldn't work. So for us, we were not able to use the existing embedding APIs, but we had to have our own. And so we're building our own that we will be putting into the WebKit repository in good time. So if you were to look into the WebCore directory today, you would see some interesting pound defines, things for like platform Chromium, which represents changes that we made to WebKit to support Chromium-specific things. Platform Skia, again, for Skia-specific things. Basically, WebCore has a graphics layer where you are to implement a graphics context. And so we have a Skia implementation of the graphics context. Use V8 is the pound define to select V8. And the V8 bindings all live inside of WebCore, mostly. WebKit versions. When we shipped Chrome 1, when we did our initial launch, we were very nervous about our selection of the version of WebKit. We wanted to make sure that we didn't inadvertently introduce web compatibility issues. So Safari 3 had shipped earlier in the year, and we chose to continue shipping a WebKit based on the version of WebKit that Safari 3 shipped, mostly just to achieve compatibility. We didn't want to worry about being on a different WebKit that had changed. And again, for Chrome 2, we're pretty lined up with Safari 4's WebKit. I think we've taken a slightly newer version of WebKit than they shipped. And one of the big hurdles for Chrome 2 was actually moving from this older WebKit to the newer WebKit. And so that has a lot to do with what I want to talk about next. So WebKit development. So members of the Chromium team are very active in the WebKit community now. We have a number of reviewers, a number of contributors, and we're just trying to increase our presence there and increase our contribution to the WebKit project. So we believe strongly in WebKit being, we're very happy to have used WebKit. We're just very much enjoying all the things it does for us, and we want to continue to contribute to it. I say status unforked. So when we initially launched, because we were on an older version of WebKit and we needed to fix problems, we were accumulated a large number of forks to WebKit. And indeed, to even support V8 in WebKit, we needed to make modifications. So in order to get to a point where we could actually work directly on WebKit and be a first-class citizen in the WebKit world, we needed to unfork. And so we went through this massive undertaking to sort of push all of our changes into WebKit and refactor things so that our changes could live there, and finally end up in a world where we're able to work with Chrome, develop Chrome on the tip of tree of WebKit alongside of other developers who are developing tip of tree WebKit using Safari. So our focus on WebKit development going forward is, as I mentioned before, we want to establish a WebKit API for Chromium. Our goals here are very simple. We want to build a very simple C++ API to WebKit that that's not dependent on any other toolkit other than WebCore, right? That's basically just about a very thin layer to WebKit so that if anybody else wants to embed WebKit, they have an easy path forward. It's not a matter of picking a certain flavor of toolkit that is compatible with your world. But here, suppose you just want a simple API that's not particular, you could use this as well. We have a lot of folks working on Open Web Platform, HTML5, et cetera. Web Workers is included in that, and a number of other things like the video feature that was just recently launched in the Chrome Developer Channel. And of course, we're very interested in improving WebCompat. I think WebCompat is probably one of the number one challenges for any fledgling browser, certainly for any rendering engine that doesn't have the kind of market share that MS-HTML has or Gecko has. And so the things that we can do here to make a difference, I think, will go a long way. I think WebKit is fortunately getting to the point now where it's approaching 10% market share if you add up all the browsers, mobile included, that embed WebKit. And so my experience with Firefox tells me that once you get to that 10% point, that's when people don't have a choice but to care, because if 1 out of 10 users to their website can't view their website or can't purchase something off of their site, well, then they'll feel that in a financial manner at least. And so the hope is that once you reach that threshold, suddenly it'll be a snowball effect, and people will care, and compatibility problems will disappear faster. And of course, we continue to be very interested in how we can improve performance. Performance and speed is important to the whole essence of Chrome. Open Web Platform, just a few more notes about that. Some of the things that are in progress. Audio, video, well, you saw the recent release, and we're very excited about that. There's lots more that can be done to improve the HTML5 video support in Chrome. So we'll be working on that. Application cache, database, local storage, session storage. These are all features about enabling offline applications. So very excited to adopt the same APIs as all the other major browsers. Some of these things are already enabled in WebKit. So you might say, well, how come Chrome doesn't have them already? Safari 4 has it. And it turns out that when you throw a sandbox around the rendering engine and you divide it up into multiple processes, that some of these things are become much more complicated to support. What do these have in common? Well, application cache, database, local storage, they're all touching the disk. So there's file system access. File system access that needs to be proxied or managed in some way so that these rendering processes can securely access these APIs. So these are all in development, and the way we tend to develop new features in Chrome is that we put them into the main line, but behind a command line flag, so that they're not actually enabled by default until they're ready. But by having them in the main line, it means that as dev channel releases go out, beta channel releases go out, or stable pushes even happen, these features are there, and people who are interested can set the command line option to turn it on, to try it out, to give us feedback. So we don't have to require people to do custom builds in order to try out new features and give us feedback. They can just take the standard build, try it out, give us feedback. This is huge for supporting a community of testers. Notifications is a new thing that has a lot of interest. It's all about trying to make it possible for web applications to do better notifications to the user, better than window.alert. Window.alert is a very unfortunate API. It sure would be nice if Calendar could have a less annoying, a less obtrusive way of notifying the user that there is a meeting coming up, but a notification that is still effective at getting your attention. So that's the kind of stuff that we're working on. And of course, web workers I talked about before. There's this idea of shared workers, which is really interesting. That's still being worked out. Details are being worked out, but sure it would be very powerful if you could have a worker that lives on beyond. Well, I should back up and make sure everybody's familiar with workers. This is the idea of background threads where you can run JavaScript on. A dedicated worker is one that a web page just creates for itself, so it wants a background thread. He can create a dedicated worker. When the page goes away, the dedicated worker goes away. Persistent workers, well, the worker can live on a little longer. But shared workers are kind of like persistent workers, but different in that they have a name, and you can find them lazily. You can find them and connect to them. And so it could give web applications this very powerful way to have a context, a JavaScript context that's hidden and off to the side that they can later connect to. So you can imagine a web application might run a portion of its back end there in a shared worker and let the actual web pages just be front ends that render the data that shared worker manages. So there's a lot of really interesting ideas in HTML5 and Open Web Platform that we're very excited to be implementing. So I just want to briefly talk about the network stack, since I mentioned before that's a very important element of browser architecture, making a better wheel. So one wonders why go and invent another networking stack? There's so many out there. Indeed, when we first started the project, we thought, well, let's not do this. Let's not write this code if we don't have to. And in fact, can't we just use the networking stacks that ship with the various operating systems that we wish to target? So on Windows, the natural choice is probably WinINet. That's the networking stack under the hood of Internet Explorer. And there's an API to that's well established, and so let's use that. And we started down that path, and interestingly enough, we learned that we really needed to have control over our own web cache and our own cookie store. Okay, so WinINet, you tell it, don't use your cookies, we'll supply our own. Turning off the cache, though, turned out to be kind of difficult. Well, we wanted to be able to turn off the cache because we needed to be able to support incognito mode. We wanted to be able to turn off the cache because, well, if the cache contained data that was fetched by Internet Explorer, then it might be data specific to Internet Explorer's user agent string. And so that could be a problem. So we really are in a situation where we have to manage our own cache. And it turns out that there was no way to tell WinINet, hey, look, I don't want you to supply data from your cache. And so we then switched to WinHTTP, which is another library that Microsoft ships that just provides the HTTP layer. You bring your own cache, you bring your own cookies. Okay, that sounds great. And that's actually what we shipped with in Chrome 1. But we recognized that we were missing opportunities to improve performance, missing opportunities to improve this layer, and even to fix certain bugs. And so we set about developing our own library, and that now lives in SourceNet HTTP in the Chromium codebase. And that's what's shipped in Chrome 2. So DNS prefetching is something we shipped in Chrome 1 you've probably heard about, which is all about predicting which host names you might visit so that we can get the DNS resolve started earlier. This has a very measurable impact on performance. And so and we've been spending a lot of energy. Whenever anybody checks the little thing, help supply anonymous usage data to Google to make Google Chrome better, that anonymous data is used to help support tailoring these kinds of algorithms, understanding when this is working, when it's not working, and various other aspects of Chrome as well. So in development, there's lots of things still to be done for the new network stack, feature parity, and there's things missing like SOC support, IPv6 literals. Regular IPv6, if a hostname resolves to IPv6, would work fine, but if you actually use an IPv6 literal, there's some little subtle bugs. And working out all those kinks are things that are happening for future releases. Other cool new features that might help, that will have a big impact on performance, sparse caching. So video support really demands the idea that you should be able to advance the movie to a certain location and start downloading from there and cache all that data. Well, we want to still be able to jump back to the old location and hit the cache again. Sparse caching is going to help with this a lot. This will also improve the way Acrobat Reader runs inside of Chrome, because Acrobat Reader, when you advance to a page like the 27th page, Acrobat Reader will ask the browser, please fetch me the data at this range. And so we want to be able to cache that. Other browsers don't cache the ranges like that because managing a sparse cache is actually pretty complicated. There's a bunch of other ideas we have that we're brewing and trying to actually test out, looking at ways that we can actually employ HTTP pipelining in a manner that's safe, looking at ways that we can improve the establishment of TCP connections, because these are TCP connection establishment is a point at which you can really lose a lot of time. And if anything you can do to kind of like hide that time or avoid paying that cost, when the user actually tries to go somewhere, it would be beneficial. But of course, we have to be very careful not to put too much burden on servers and things like that. So parallel proxy autoconfig, well, if you're ever using proxy autoconfig, you know that performance can be a real problem with it. And so all of us at Google use a proxy autoconfig, and so we feel this pain every day, and so we really want to do something about it. And hopefully it benefits other people as well. And that's it. I want to open the floor to questions, and let me know what you're interested in.
Hi. As a script developer in JavaScript, I'm not that familiar with the Chrome yet. When I write a XML HTTP request, I can do it synchronous or asynchronous, and the synchronous is usually blocking, at least on IE. The new Firefox, I realized it's non-blocking. Is it the same with Chrome?
So it turns out that that's a very interesting thing you mentioned. I'm actually the developer who implemented Firefox's behavior, and I kind of regret it, and I'll explain why. Because JavaScript has the assumption of run to completion, of being single-threaded. But if JavaScript blocks on XML HTTP request to do a synchronous network I/O, it still looks like a function call to JavaScript. And if you interrupt that function call with like running another JavaScript, some other thread of JavaScript somewhere, I mean, it's all on the same real thread, but to the programmer, it looks like somehow JavaScript in another context was running in the middle of this function call. And so it breaks the run to completion behavior that you come to expect. And so I worry that the Firefox implementation, I was a fan of it at the time because it frees the UI from being locked up. But I worry that it would result in some very strange bugs for web developers, because when they expect their program to just run like a sequential program, it's suddenly not. And so it is a very big concern to me. In Chrome, we took the approach of, well, the rendering engine is a child process, and we have a bitmap of the recent representation of it. So when the web page says XML HTTP request send in a synchronous manner, we just let that process suspend itself. And during that I/O time, we show the old representation of the page. Of course, the page is not interactive at this time. But I feel like that's probably the right way for it to behave. And basically, my belief is that synchronous XHR is really a pretty evil API. It's not one that works well with the web. The web is asynchronous. Asynchronous APIs work much more naturally in a browser environment. So that's, I can imagine Chrome doing smarter things, though, in the future, like, for example, giving the user some UI so that they could interrupt a synchronous XHR that's taking too long. Today, the only way to interrupt a synchronous XHR in Chrome that's taking too long is to close the tab. Close the tab, we kill the process. But if you could interrupt it and return control to JavaScript with an error, that seems like it would be better. Any other questions?
I almost want to encourage you to do some alternative to NP-API. I've struggled with trying to port across the different browsers on PGP, and we've been trying to do something to look at secure text, encrypted like an embedded encrypted content, and display it. It was really difficult to go across the different browsers. There's a lot of little fallbacks, NP-API. Well, put it this way, if you're going to do it, could you at least put out some sample code, one that compiles and actually works in the different browsers and does something?
I agree with you. NP-API is really the bane of developers who have to deal with it. I wish there was something better as well.
Well, I mean, even the Safari, WebKit plugin thing is at least that works on Safari. Maybe leverage some of that.
Mm-hmm. Yeah, I'm very interested in a better solution, and one that is well documented and full of samples that actually make sense. Next question.
I have a question about your strategy for increasing compatibility, like with rendering in Safari. It seems like in Safari, when they're about to make a release, they do like a WebKit tag, and then maybe they commit into that tag. What do you do to ensure that your whatever you do before release is compatible with their rendering?
If I understood the question right, you're saying what happens if a new tag is introduced that's sort of half-baked?
Or what do you do, I guess what's your strategy before, when you're deciding on, what revision to go off of?
Yes. Okay, yeah, so it's a very tough question. Because we are trying to release early, release often, and not just be beholden to when Apple decides to launch WebKit, it does mean that we potentially pick up half-baked APIs, half-baked things. But fortunately, the way WebKit community tends to work is that they hide those things behind a pound define. And so it's up to us to decide when to add that pound define so that it's compiled in. And that's basically been our approach. Yeah. So we don't expose them until we're ready.
I was curious a little bit more about the sandboxing. You were saying in Windows it kind of strips the credentials away from it, and I was curious about other operating systems, if it would be more of a memory bounds checking at the code level, or if you're familiar with Valgrind, which is object code, how would you be implementing that?
There's a lot of crazy ideas on afoot for how to sandbox on Linux. You have a lot of traditional tools like chroot, different user, a totally different user. There's a lot of things, but all of those tools seem to require some change or some support from the host system. So something that's installed by admin or whatnot. I would encourage you to get up on Chromium Dev and chat with the engineers who are actually looking into this problem, because there's just so many different approaches you could take with
Are you guys
sandbox.
interested in any sort of it's not really portable, but it's like an object type, like how Valgrind does it, where it just reads object code and just runs that inside of an emulator, like a user space emulation?
Big concern is performance, really, with anything we do.
Okay, thank you.
Hey, one more thing about plugins. It would also help if maybe you streamline the installation process a little bit. I understand the security implications of having plugins. It'd be nice from a user's point of view if they could click somewhere and actually get a plugin and without
yeah,
having
sure.
to reboot the browser. And
Well, one of the things we're trying to solve with Chrome extension system is to actually make it easy for extensions to deliver all manner of things that extend the browser. And so just like an XPI can be used on Mozilla to deliver an NPAPI plugin, a Chrome extension bundle should be able to do the same and give the user very good control over managing that plugin.
yeah, we'll talk offline.
So anyways, that's it. I'm afraid we're all out of time for questions, but I'm happy to talk to folks afterwards. Thank you so much for coming, and I'm to remind you of this, haveasec.com/io. Please leave your comments.